Hello, it's Bill again. And today, in Max's Come Discover Gravity series, we're going to talk about special relativity and lambda. We're going to see how dark energy actually relates to special relativity. Now here we have a twins paradox thought experiment. We have Bob and Alice at Earth, and we have a distant star. And there's about 10 billion light years distance between Alice and that star. And that means because of that distance, dark energy is going to be pulling those objects away at 0.7 c. So that distant star will have a 0.7 c recessional velocity relative to Bob on Earth. So Alice at T1 flies 0.8 c. But because of the separation of 10 billion light years, Alice can only make progress at 0.1 c. But let's say at time 2, Alice still flying at 0.8 c, but now the separation is only 5 billion light years between the distant star and Alice. So now Alice makes progress at 0.443 c because the recessional velocity of that star at 5 billion light years is 0.35. And then at time 3, Alice is still flying at 0.8 c, but now there's zero separation. So the recessional velocity of that star is now 0. So Alice makes the full progress at 0.8 c. And this is kind of from Alice's perspective. Now remember, in our gravity videos, every particle has its own cosmic horizon that moves with it. So when Alice is flying through the universe, her cosmic horizon is following her. So this time we're going to mix it up a little bit different though. We've got a new thought experiment. This time we're going to have 11.18 billion light years separation. Now this is going to cause a 0.8 c recessional velocity. So 0.8 times the speed of light is the recessional velocity of that star relative to Alice and Bob. So on time 1, Alice starts flying at 0.8 c, but because of that separation, Alice cannot make any progress. Now Bob here is going to go zipping by in the background because Alice is moving at 0.8 c, but this star is going to appear to be stuck. It's just going to float there and not have any Doppler shift even though Alice is flying at 0.8 c. So it appears that that star is forever stationary from Alice's perspective. She never gets closer than 11.18 billion light years away from that star. And that's because Alice's cosmic horizon moves with her, shifting her causal boundary through the lambda field. And this cosmic horizon is what creates that lambda field. And you could look at it this way. From Alice's view, it looks like this star is riding her cosmic horizon relative gravity well. So her horizon is moving at 0.8 c, but it's dragging this star along. So Alice really never makes any progress towards that star. Now we'll look at it from the other direction. We're going to go out to the star and put a little alien out there, Klaatu, and see how he perceives things. So Klaatu sees that Alice is close to his horizon, and Alice is burning at 0.8 c to escape falling back over Klaatu's horizon. So remember, before Alice thinks that Klaatu is surfing her cosmic horizon and always forever staying out of reach. But in this case, it looks like to Klaatu that Alice is trying hard as she can to remain relevant in Klaatu's universe. So over time, Klaatu is going to see Bob fall behind his observable universe, lost forever, and Alice at that point will never be able to meet up with Bob. So if you do the classical twins paradox calculation without dealing with dark energy, there's a big problem. You see here that with the classic one, we have 28.57 billion light years for Alice traveling at 0.7c. Return trip, 40 billion light years. But the problem is, at this 10 billion light year separation, we have 0.711 separation. So that means that Alice will never make it to that star. That star will keep on receding. And Alice will never make it back to Bob. If Alice goes all the way out to where that star was and then tries to turn back around and make it back to Bob, she will never see Bob again. Alice and Bob will be forever out of contact with each other. So, anytime you're going to do a special relativity calculation, you really need to add in the effects, find out the effects of dark energy, because dark energy is going to definitely affect the answer. So before a twins paradox can properly be framed, one must first determine the amount of dark energy present in the universe. This reveals where the cosmic horizons exist, allowing accurate calculation of both recessional velocities and the effects of reference frame acceleration. Only with this information can one reliably compute travel times and ensure that distant objects within causal reach. For centuries, physicists have asked, what does a local observer move through if space is not a substance? The answer is, a traveler is not moving through space as a medium, but is instead continuously matching velocity against the recessional velocities of distant regions within their observable universe. So this part right here, this is the part that connects general relativity to special relativity through the effects of the cosmic horizon. In a lambda-driven cosmos, motion is not measured against a static backdrop. It's measured against an expanding horizon-defined relational geometry. To move is to overcome recession. To stand still is to be balanced against the universe's own stretching fabric. So if you're not moving at all in your frame, you're not matching any recessional velocity, then everything is pulling away from you at an equal rate. But once you start moving one direction, you start matching recession velocities with distant objects and regions, and that kind of skews the frame to where things behind you recede faster and things in front of you seem to maintain position. And also consider that when Alice is flying at 0.8c at a 10 billion light year separation, that remember how she started off looking like she was only making 0.1c progress, and then it went up to like 0.5c progress, but she only saw 0.8c when she actually made it there. So even though Alice had the same speed, you could see the acceleration geometry relative to that distant object. And this is how special relativity under Lambda geometry behaves. Thank you very much and have a great day. Check out my other videos. I'm going to put this one in the playlist as well, and if you have any questions, please write them down in the comments, and we'll talk to you soon. Bye-bye.